Welcome to the Explainer. I am absolutely thrilled you're tuning in today because we're tackling what is easily one of the most frustrating bottlenecks in modern tech, turning messy, sensitive, real-world documents into perfectly typed, usable database rows. And we're going to look at exactly how to build a highly capable, completely private AI architecture to do just that. We're calling this the boring is beautiful reference architecture. By the end of this explainer, you'll see exactly why wildly boring infrastructure is actually the secret weapon to running cutting-edge AI. It's literally the million-dollar question, right? How do you process documents with AI without your data ever leaving the building? Because relying on external cloud APIs brings constant, massive headaches. We're talking rate capacity limits, totally unpredictable pricing, and huge data governance risks. So, we're going to explore the ultimate fix to those problems by running the whole shebang locally. Okay, let's dive into this. Here is our structural roadmap so you know exactly how we'll break this down. First, the local AI imperative. Next, the 4 core design principles. Then, we'll map out the 5-stage pipeline, tackle the 7% problem, and finally, we'll look at when to walk away. All right, section 1, the local AI imperative. Why build locally and why now? Well, 4 converging facts are driving this massive shift. First off, models have simply gotten incredibly good on local hardware. We're talking about free 3 billion parameter models that can read 40 pages in a single pass. It's wild. Second, regulations like the AI Act actually reward keeping your data inside your own building, which just massively simplifies your data governance stack. Third, relying on someone else's server capacity or external vendor policies is a huge operational liability. I mean, when they go down, you go down. And finally, the memory market has shifted so much that you just don't need massive remote parameter counts to get the job done anymore. This is an engineering reality now, not just some pipe dream. Moving into section 2, 4 core design principles. Before we map out any pipeline arrows, we have to set the rules. Now, what's really interesting here is how contrasting highly modern AI with wildly traditional, boring infrastructure creates rock-solid reliability. Principle 1. The model is an appliance. It is not an orchestrating framework. It takes pixels in, it spits text out. It doesn't retry, it doesn't talk to the database. If your model orchestrates, your pipeline will rot the second that model is deprecated. Principle 2. Python stays strictly at the machine learning boundary as a narrow command line interface. Read an input, write some JSON, exit. Principle 3. The architecture literally is a 150-line Postgres queue database queue. No Redis, no RabbitMQ, just a rock-solid, crash-safe jobs table. And finally, idempotency is guaranteed by a content hash. Every document is identified by a hash of its contents, which makes retries perfectly 100% safe. Section 3. The 5-stage pipeline, the document's journey. We're now going to follow a single document step-by-step through the mechanical heart of this architecture. Here's the bird's eye view. We ingest, we run OCR, hit a central queue, extract structured data, and securely store it. Let's see exactly how a highly sensitive PDF becomes a safely stored database row. So, stage 1 is ingest and normalize. This is where the original bytes are written to storage and the content is hashed. If it's a PDF, it gets converted into per-page PNG images at roughly 300 dots per inch. Why 300 dpi? Well, because that is the exact resolution floor where OCR quality starts to quietly degrade. Notice that absolutely nothing intelligent happens here. This ingestion phase should be completely boring. It needs to be too boring to fail. Then we hit stage 2, which is optical character recognition, OCR, acting as a narrow command line interface. Listen, model choice here is a routing decision. It's not a religion. For instance, if cross-page structure really matters, think contracts or multi-page reports, you'd probably route that to a multi-page context model like unlimited OCR. But if you have physically degraded, messy, single-page inputs, specialized models like the Paddle OCR VLs class have vastly superior accuracy. And because the command line contract is identical, swapping these out is just a simple config change. Your pipeline shouldn't even blink. Next up is stage 3, the queue in the middle. So the crucial point is that we manage traffic using a simple Postgres jobs table, utilizing the skip locked command. Just 3 simple features do all the heavy lifting here. First, Bay max attempts threshold stops infinite retries by routing repeat failures straight to a dead letter status. Second, a lock timeout sweep safely reclaims jobs if a worker crashes. And third, per-type concurrency caps ensure that a massive 40-page job doesn't blindly compete for GPU resources with a tiny 1-page job. It gives you incredible operational control, and you didn't even have to add complex new software surfaces to monitor. Moving to stage 4, structured extraction.
Your OCR output is Markdown? Sure, but your business? It runs on typed database fields. You absolutely must avoid the magical single-step approach that collapses transcription and extraction into one big prompt. Why? Because it makes errors completely undebuggable. Instead, we use two passes. You use a local daily driver LLM to read the markdown and extract the typed fields against an explicit schema. Deliberately separating that OCR phase from the LLM extraction phase means you can fix transcription errors and schema errors independently. And that brings us to stage 5, storage with provenance. Provenance is an absolutely critical term here. It means the exact origin details of your extracted data. You store the source document hash, the page span, the model identifiers, timestamps, and a confidence score right alongside the data itself. To put that into perspective, when an auditor inevitably questions a number 8 months from now, these provenance columns mean the difference between running a simple database query and launching a massive, painful archaeology project.
All right, section 4, the 7% problem. Exceptions are the product. Let's slow down the pacing for a second here, because we have to talk about reality. AI isn't perfect. A 93% pipeline success rate, that is fantastic, but it means the true design challenge, the real engineering work, is the remaining 7% of unparsable pages or extractions that fall below your confidence threshold.
So how do we handle that 7%? Well, low-confidence extractions and schema failures are automatically routed to a human review queue. A real person sees the page image and the extracted candidate side by side, and they correct it. But here is the absolute genius part. Those corrections are stored as data. This highly focused human role actually builds the exact ground truth training and evaluation set you are going to need for your next model swap. It's a brilliant feedback loop.
Section 5, when to walk away, setting the boundaries. Because we need to be realistic.
This architecture is incredibly powerful, no doubt about it. But it's not a universal magic bullet. If your monthly document page volume is below 10 to 20,000 pages, honestly, walk away. At that low volume, commercial OCR API costs are simply cheaper than the engineering time required to build and maintain this pipeline locally. This architecture earns its keep on high volume, high data sensitivity, or ideally, both. Let's move on and see how this builds into some specific scenarios where a cloud tier or a totally different robustness plan is honestly just the better recommendation. First, if you just need standard, pre-built key-value extraction for standard invoices or IDs, cloud providers already ship the schema and training for that out of the box. Second, if your inputs are warped, skewed, crumpled photographs of physical paper taken from a cell phone, the models favored by this pipeline drop hard on crumpled receipts, you'd need a totally different setup. And third, if nobody on your team is actually dedicated to owning, patching, and monitoring the infrastructure, if you don't have an ops person, buy a cloud API. You're actually just paying for their ops team. We also really need to clarify the legal compliance reality here, impartially. Local pipelines remove a huge compliance burden. You don't have to deal with third-party vendor subprocessor audits or third-country transfer analysis for your sensitive documents. But, and this is a very big but, GDPR or DSGVO still applies exactly as it would to a SaaS product. You are still processing data. You still have to manage purpose limitation, data retention schedules, and strict access controls on your Postgres tables.
It all comes down to this simple reality. Local first simplifies compliance. It never waives it. That is the absolutely critical legal and operational takeaway of this entire architecture. You are taking ownership of your data, which gives you immense power and simplicity for sure, but the responsibility, that remains entirely yours.
Which leaves us with this final provocative thought to consider. Is your AI pipeline built to survive the next model generation, or will it rot with it? By relying on boring, bulletproof infrastructure like Postgres queues and keeping the models as swappable, narrow CLI appliances, you ensure genuine longevity and discipline in your data infrastructure. Thank you so much for joining me for this explainer. I really hope this gives you a completely new perspective on building resilient, local AI.